Hello students, this is the fourth of 4 free fall videos. The first was a general introduction to free fall problems, and then this is the third example problem where we will be finding how fast the object is going. There are 3 typical types of free fall problems, one where you find out how far it falls, one where you find out how long it takes, another kind where you find out how fast it's going. I probably could have divided this one into 2 separate videos because sometimes you have to find out how fast the object is going and you know how long it took to fall, meaning you know the time, and sometimes you have to find out how fast it's going and you know how far it has fallen, so you know the distance. This is that kind of problem where you have to find how fast the object is going after it has fallen a certain distance. I think that's the harder of the two, so I decided to show you that kind, but I will also be mentioning the other kind, where you have to find out how fast it's going after a certain amount of time, as we're moving through this one. As with all problem solving, you're going to read through the problem carefully, making note of the information that you have, and the piece of information that you're looking for. This one says, passengers on the Giant Drop at the Dreamworld theme park in Australia are dropped from a height of 115 meters and are in free fall over a distance of 71.7 meters before enormous magnets slow and stop the carriage. How fast are the passengers traveling after falling 71.7 meters? This problem has a piece of information that we're not going to use, that is the 115 meter distance. Although they are raised to that height up off the ground and they get back to the ground, so eventually they fall from that height, they're not in free fall for that entire time, because after they've fallen 71.7 meters, these magnets take over and slow them down. So we're only interested in the free fall portion, so we're only interested in the distance 71.7 meters. So that is our displacement, 71.7 meters. As in all free fall problems, we assume they're taking place on Earth, and on Earth all objects fall with the same acceleration, 9.8 meters per second squared. So if they're moving toward the Earth, they speed up with that acceleration. If they're moving away from the Earth, they slow down with that acceleration. It's convenient in this problem to take the downward direction as the positive direction. So our displacement will be positive 71.7 and our acceleration will be positive 9.81. We know how these kinds of rides work. You're lifted up to the top of the ride where you pause for a moment and you are not moving, and then the carriage or whatever you're sitting in is disengaged and you fall. And so it makes sense to assume that the initial velocity is equal to 0. So as in most free fall problems, this piece of information and this piece of information are assumed to be true, although they're not explicitly stated in the description that you're given for the problem. This problem says asks how fast are the passengers traveling. So we're trying to find out a velocity. It's important to recognize that you're trying to find out the velocity at the end of the acceleration. You're trying to find out the velocity at the end of the free fall. So you're actually trying to find the final velocity, not the average velocity. Okay, lots of people would possibly be able to look at the equations and know right away which one to pick. If that's the case, then pick your equation and move on to the algebra. If you get stuck here, you don't know which equation to pick. What I typically do is put a little check mark by all the pieces of information that I know in those equations. So I know delta x and vi and a. So I'm going to check off those things. Delta x and vi and a. Okay, and then I look through the equations, figuring out which ones it's even possible to use, and then if it's possible to use more than one, I figure out which one is best for the problem that I am working on. So it's not possible to use the first equation. I don't know V average or T. It's not possible to use the second equation. I don't know V average or VF. It's not possible to use the third equation. I don't know T or VF. It is possible to use the fourth equation. I have VI and I have A and I have delta X. So I can use the fourth equation to find VF. And since that's what I'm being asked to find, that's the equation that I'm going to use to solve this problem. I have enough information to use the last equation as well, but that one would allow me to find the time. And that's not something that they're asking me for. They're not asking me how long they're in free fall. They're asking me how fast they're going after the free fall portion is over. So it's possible to use this equation, but it gets me to a piece of information that I'm not being asked to find. I mentioned at the beginning that you can find out how fast the object is going if you know how far it fell or if you know how long it took. So we know how far it fell, so we're going to be using this equation. But if we knew how long it took, instead, if we knew the time, then we would have this value instead of delta x, and we would use this equation to find the final velocity. So if you're being asked how fast is it going after it falls for a certain amount of time, then the third equation is the best one to use. We're being asked to find how fast it's going after it falls a certain distance, so the fourth equation is the best one to use. All right, so we're picking the fourth equation. VF squared equals VI squared plus 2 times A times delta X. So VF squared is equal to VI squared. Another situation where, since the initial velocity is 0, squaring that 0 is still 0. And so this term in the equation is 0 and disappears when we actually get down to doing the math. 2 times 9.81 meters per second squared, and our delta x is 71.7 meters. VF squared equals 2 times 9.81 times 71.7. The 2 is part of the equation, and it is an exact number, so that does not limit my significant figures. Both of the measurements in my problem have 3 significant figures, so I'll write my answer down with 3 significant figures. So the number 1,406 written with 3 significant figures would be 1,410. Now the meters times the meters will make meters squared, and I already have seconds squared in the denominator. This is not the answer. This is equal to VF squared, and I was asked how fast are they going, so I want just the final velocity, not the final velocity squared. So now I'm going to take the square root of both sides to get VF. So I'm not going to clear out this number 1406.754 from my calculator and then retype it in as 1410. I'm just going to leave it in my calculator and do my rounding at the end. So I want to have the square root of this number. So I was telling you before that I hit the exponent number and then raise it to the 0.5 power. That's the same as taking the square root. And that's equal to 37.5 with 3 significant figures. 37.5. When I take the square root of the number, I'm also taking the square root of the units. So the square root of meters squared is meters, divided by the square root of seconds squared is seconds. So I have the units meters per second, as I would expect for a speed. So how fast are they going after they are in free fall for 71.7 meters? 37.5 meters per second.